Hi, this is Presh Talwalkar. A group of people decide to play Secret Santa. To begin, each person writes their name on a piece of paper and places that paper into a hat. Each person then takes a name from the hat at random, and that's the person to give a gift to. The draw is successful if everyone gets a different name. So your puzzle is what's the probability of having a successful draw? That is, what's the chance that no one gets his or her own name? In the draw illustrated, each person is getting a different name. But you could imagine there's a different type of draw where, say, person D gets his own name. This is not permissible because you don't want to be giving a gift to yourself. So this is an unsuccessful draw. So your problem is to figure out what's the probability of a successful draw. And you need to solve this for a group of n people. Give this puzzle a try, and when you're ready, keep watching the video for the solution. So first we'll count the total number of draws that are possible. The first person can draw any of the n names from the group. The second person can draw any of the remaining names. So since one name has already been taken, there are n-1 names that are remaining. The third person can draw from any of the n-2 remaining names that have not been taken by the first or second person. The very last person will be stuck with just the one name that's remaining. To count the total number of draws that are possible, we multiply the number of possibilities that each person can draw. This will be the familiar formula of n factorial, which is the product from 1 to n. Now we need to count the number of draws that are successful. So if you try and count this up, like the first person can select any of the n-1 names, but not his own name. The second person can select any of the remaining names, hopefully not his own name, and hopefully that first person hasn't already selected his name. The very last person has one name remaining, and hopefully that name is not his own. So if you try and count this up, it's going to be kind of complicated, so it's going to be difficult to count. So the trick in this puzzle is you want to count the number of draws which are unsuccessful. That is, you have at least one person picking his own name. So what we're going to do is we're going to count the number of ways at least k people choose their own names. In order to do that, we're going to need the binomial coefficient, n choose k, which is the number of ways that you can choose k items from a group of n. How many ways will at least one person get their own name? Well, if one person gets their own name, there are n-1 arrangements of the remaining people. So that becomes n-1 factorial. There are also n choose 1 ways of picking that one person. Similarly, you can count the number of ways at least 2 people get their own name. There are n choose 2 ways to pick those 2 people, and the remaining n-2 people can be arranged in n-2 factorial ways. So this pattern continues. And in general, we can say that at least k people get their own name. We're going to multiply the number of ways of choosing those k people, which is n choose k, times the number of ways to arrange the remaining possibilities, which is n-k factorial. So when you simplify this formula, you get n factorial divided by k factorial. And we're going to keep that formula. So we have at least k people getting their own name is equal to n factorial over k factorial. So now we want to know how many of the draws are unsuccessful. So we've been counting at least k people getting their own name. What we really want is exactly k people getting their own name. So we want to add up at least exactly 1 person, exactly 2 person, and so on. So how are we going to do this? We're going to avoid double counting by using the inclusion and exclusion principle. We add up the numbers where they're the number of sets which have an odd number of people, and we subtract out the sets which have an even number of people. So this is the formula. We add up the ones where at least 1 people are getting their own name. We subtract out at least 2 people. Then we add back in having at least 3 people, and so on. We subtract out the number of sets which have at least an even number, and we add in the numbers which have an odd number. So you may remember this from like a Venn diagram. If you want the probability of A or B, you take the probability of A plus the probability of B, and you subtract out the probability of A and B. So, when we substitute our formula into this inclusion-exclusion principle, we end up with the alternating series of n factorial divided by the reciprocal of factorials. We can factor out n factorial, and we have the alternating sum of the reciprocals of factorials. So these are the total number of ways, the total number of draws that are unsuccessful. We can find the probability of an unsuccessful draw by dividing by the total number of ways, which is n factorial. So that'll remove the n factorial term, and so we have the alternating sum of factorials is equal to the probability that we have an unsuccessful draw. Now to get a successful draw, we take 1 minus the probability of an unsuccessful draw. So that removes the first term, and we have the alternating sum of the reciprocals of factorials starting at 1 over 2 factorial. And this is an interesting sum. This is going to be equal to approximately 37% because this is the power series for e to the power of -1, or 1 over e. So there are many interesting things about this. One is that we have the constant e, which seems to come out of nowhere. The second thing is we have a 37% chance, and that's going to be fixed pretty much no matter what size n you have. It's approximately going to be 37%. Did you figure it out? Thanks for watching this video. Please subscribe to my channel. I make videos on math and game theory. You can catch me on my blog, Mind Your Decisions, which you can follow on Facebook, Google+, and Patreon. You can catch me on social media at Presh Talwalkar. And if you like this video, please check out my books. There are links in the video description.